recently did a project where I needed to find the intersection points between two lines, so I did some research and came up with a script for Blender that does just that. In this video, I'll show you how to write a Python script that allows you to find the intersection point between any two grease pencil strokes. First, let's set up a Blender scene to test with. We'll launch Blender in 2D animation mode and split our view so that we have a text editor on the right side. Then we'll create a new text file. The first thing that we need to do is to import the BPY library so we can access the Blender Python API. Next, we'll have it work on the selected object, verify that the object is a grease pencil object, and then tunnel down through the layers and frames to get to the strokes. For now, we'll hard code it to only deal with the first two strokes, and we'll assign each of the strokes to its own variable, stroke 1 and stroke 2. For our lines, we'll use the line tool to draw two grease pencil lines that overlap. If we switch to edit mode and point selection, we can see that the lines drawn by the line tool come with multiple points by default. But in order to keep things as simple as possible, we'll want to remove the middle points so that there are only 2 points per line. We can do this by selecting the middle points and using the dissolve option. This removes the points but keeps the line. Now we should have 2 lines with 2 points each. Next, we'll extract out the position of both points on a line. We do this by referencing the stroke's points attribute. For now, we'll assume that the stroke only has 2 points so it's easier to work with, but we'll make this more generic later on. Since we assume that we only have 2 points on each of our lines, we can get to the 2-point positions by querying the .co attribute on index 0 and 1 of our stroke points for each stroke. With the point position of our lines in hand, we're ready to start building our function to find the line intersections. The only thing this function needs to know is where each line starts and ends, so we'll create 4 parameters. The first 2 are the first line's start and end positions, and the second 2 are the second line's start and end positions. Because we got the point position values by querying the .co attribute on the stroke point, these variables contain a tuple representing the x, y, and z positions of the points. To keep our heads from exploding, we'll treat our lines as 2-dimensional, so we'll ignore the y position, which is the depth of the point. But in order to feed these values into our formula, we need to tease apart the x and z values for each point into their own variable. This will give us 8 variables in total, an x and z position for each of our 4 points. Now we're ready to start building the formula to calculate the intersection points. The simplest formula I could find for calculating the intersection between 2 lines is this. Yikes. And I won't even pretend to know the details of what's going on here, but thankfully we don't really need to. Examining the formulas broadly, we can see that there are separate formulas for figuring out the x-intersection value and the z-intersection value. The numerator for x-intersection and z-intersection are nearly identical, with just the x's and z's swapped around a bit. We can also see that the denominators are exactly the same in both. To keep from getting too bogged down in the mathematical details, we can treat this formula as a bit of a black box and just pretend that we're dealing with a unique numerator for x and z and a comma denominator between them. As such, we can add these definitions to our script. To use these formulas, we feed in our x and z values for our points a1, a2, b1, and b2, and we return the intersection point as a tuple. If we print out the value returned by our function, we get the intersection point of these 2 lines. To visualize this intersection point better, let's mark it with a circle. We can borrow an ellipse function from an earlier tutorial and plop it into our code. Remember to also copy the import statements from the math library for pi, sine, and cosine, since we'll need those to draw the circle. Then we'll use our computed intersection points to drive the center position of the circle. Now let's give it a try. If everything's gone right, we should now get a circle marking where the 2 lines overlap. If it fails for you, double check your code. Also make sure that you have only 2 strokes in your grease pencil object and that each stroke only has 2 points, and that those points both lie on the same y plane. Now we can find the intersection point of 2 lines, but there's a couple of technicalities we need to consider. And these technicalities have to do with how lines are represented in our scene versus how lines are represented mathematically. First, it's possible that the 2 lines don't intersect at all. The mathematical definition of a line states that non-parallel lines will always meet, but parallel lines will never meet. So we'll need to account for that in our code. Secondly, the lines in our scene have discrete start and end points, but in mathematics, lines extend through 2 points to infinity. This means that in our current code, we could find an intersection point even if the lines aren't touching. This isn't necessarily a bad thing, since it might be useful to find the intersections beyond the bounds of each line, but it'd be good to be able to handle this. Let's deal with the parallel line issue first. To test this out, we'll need two parallel lines. Since it's difficult to draw perfectly parallel lines by hand, I borrowed a line function from a previous tutorial and made a quick script in a second text file. I'll include a link in the description if you'd like to follow along. If I try and run our intersection script on these two lines, I get a traceback, which tells us that we've got a division by zero error. So what's going on here? One of the interesting things about this formula is that if our lines are parallel, the denominator goes to zero. We can use this to our advantage to make our code more efficient and also avoid a traceback that would be thrown by dividing by zero, which is a no-no in mathematics. In our code, we can move the denominator definitions to before our numerator definitions, and we'll check whether it equals zero. If it does, then the lines are parallel, and so we'll dump out of our function returning a value of none. Now if we run our code again, we don't get a traceback, and no intersection point is marked. Next, we can turn our attention to the intersection points that lie beyond the lines. If I delete our parallel lines and make two lines that do not touch, and run our code, you can see that the intersection point lies beyond either line. To handle this situation, we'll give ourselves the ability to return the intersection only if the lines cross. To do this, we'll add a new Boolean parameter to our function called bounded, which we can set to true if we only want the intersection points within the bounds of the lines. Next, we'll add some checks to determine whether we're in bounds. We check the min and max of the two endpoints of each point's x and z values. If the intersection point is less than the min or greater than the max, then the intersection lies beyond our line's bounds, and we return none to pop out of the function. Now if we set our bounds parameter to true, it will not find the intersection on these two lines. But if we delete those and draw two lines that do overlap, it'll find the intersection just fine. Now that we have our function completed, we can find the intersection point between any two lines, but there's a bit of a limitation. It only checks between two sets of points per line. This is problematic since our grease pencil strokes usually have more than 2 points, so to make this script more useful, we should have it cycle through all the stroke segments and, treating them as individual lines, check for an intersection with all the segments of another stroke. To keep our code clean, we'll start a new function called findStrokeIntersections, into which we'll pass two stroke objects. We'll also add the bounded flag for whether we want the intersection points to be within the line itself. Because we're checking along the lengths of the entire stroke, we might encounter multiple intersection points, so we'll make a variable to hold any intersections we find along the way. We now need to cycle through all the points in our stroke so we can check each segment of the stroke for intersections. We access each of the points in our stroke by indexing the stroke's point attribute, and we get that point's position by querying its .co attribute. This value is then assigned to the variable p1. The second point will be the next point in the stroke, so the index will be the current index plus 1. One detail we'll want to deal with is how to handle closed strokes. That is, strokes whose endpoints connect back to the beginning, such as in a circle. In the Python API, this is determined by the stroke's useCyclic attribute. When set to true, a line is drawn between the first and last points of the stroke. Since this connection is drawn as a line for the user, we'll want to treat it as a line for which we'll want to find the intersection. To do this, we'll add a bit of logic that says if we're on the last point of the stroke and the stroke is cyclic, the second point of our line will be the first point of the stroke. Otherwise, we'll break out of our loop. If we're not on the last point of the stroke, we'll just get the next point on the stroke for our calculations. At this point, we've gathered the position for the points in our first stroke. Now we repeat this process for our second stroke, using the same logic as before but with a different iterating variable j. By the end of the second iteration loop, we should now have the 4 points that we want to use for our intersection calculations, so while we're still in the second loop, we'll call our original findLineIntersections function, and we'll pass it the 4 points representing the two segments we're comparing. Then if our function finds an intersection, we'll add it to our list of intersections. This loop continues iterating through the two-stroke segments, treating each pair of segments as two lines, and adding intersection positions to our intersection list as it finds them. Once the loops are finished, the function returns the intersections list. Down in the main part of our code, we'll change it up to pass our strokes to our new function. We can then loop through any intersections and drop a small circle at their position. Now we can catch intersections on any two strokes we want. If we delete our 2-point lines and recreate new lines, ones that have multiple segments, we can still find the intersections. What's more is it should work with any shape of stroke. We can, for instance, find the intersection of 2 squares, 2 circles, or any stroke really. Having the bounded option also creates opportunities for finding interesting geometric patterns. For example, if we create 2 overlapping circles and change our bounded option to false, it will find the intersection points for every line in the circle beyond the bounds of the circle itself, creating a cool moire effect. Now that we can find intersection points between strokes, it's just a matter of what you want to do with it. This code currently works on the first 2 strokes of a grease pencil object, but it could be easily modified to work with any 2 selected strokes, or all the strokes on the grease pencil object. I hope you found this video useful, and thanks for watching.